I'm Thorsten from Aaronia, and today I want to speak about data reduction for our SDRs. Because thanks to analog devices and some other brands, we have a lot of problems that they always give us much more bandwidth than we want, or we want more bandwidth, and how can we solve the problem with data going to our PC? Because at some point we really can't handle it anymore. So do we have a solution to reduce it? So spectrum monitoring, decoding is usually our business, and that's where we want to reduce our data. So everything I want to show is based on this project. Usually our data is coming from the ADC resolution. So if we have 10 bits, 12 bits, 16 bits, and so on, you get more data, of course. Then we have the sample rate. The higher sample rate, the more data I get. And combined with that one, we have the bandwidth. So the bigger the bandwidth, the more data I get. So in combination, I get a really, really huge data load. If I have, let's say, 1 or 2 gigahertz bandwidth with 16-bit resolution, then I really have something. So based on our products, I want to show you what we're speaking about. So we have this little Echo, for instance, which has an RX and TX, and already needs a USB 3.0 for its data transfer. That's about 500 megabyte per second. And the next one would be the Plus, that has up to 245 megahertz bandwidth, and then we already need 2 USBs in combination, so that we can get 1 gigabyte per second to the PC, which is also still handleable. The next one is the XPR, and then it gets really critical, because then we need about 2 gigabyte per second. And a lot of USB transfers have problems with that. And so already here we would need some data reduction somehow. It even gets worse with our tablet solutions. There we get about 4 gigabyte per second, and our command center, 8 gigabyte per second. Then recorders, 20 gigabyte per second, and yeah, the 19-inch racks is really the killer. And then we have 250 gigabyte or more per second. I think SETI knows about those problems. They even have much more than we have, and they are also suffering the same problem. So what do we do about it? The main problem we have at the moment is really how to get the data to the PC. So our USB limitation, Ethernet limitation, and so on. And the second problem is, of course, our CPU processing. The less data we have, the less CPU processing we need, of course. So we also have to reduce the data to bring our CPU to a low power point. And then, of course, the RAM throughput is also a big issue. If I have a lot of data, at some point it doesn't work anymore. And then, of course, if I want to record it, SSD speed, I really have a big problem recording high data loads. Just as talked before, today's laptops have some limitations. Up to 40 gig is possible, 2.5 gig with Ethernet, and the big boys have a little bit more. And if you go to the data centers, then we are speaking about 400 giga per second, but that's also limiting at some point. So, okay, how to reduce it? We have usually 3 solutions on the market at the moment. So the common one is that we simply don't send IQ data, we send FFTs or spectra with FFTs and reduce the data load by roughly a factor of 10. But of course, then we lose the IQ information, so decoding is not possible anymore. So this is a big disadvantage. The other solution is to even send less data. I think simply only send the traces instead of the FFT data. And then I can reduce the data load even more. Interesting for monitoring, of course, but then I also lose my time information, because then I only get a max hold or something like that. I have low data, of course, but at the end, for decoding and finding short signals, impossible. If I go back to IQ data, I could reduce the sample rate, of course. I still have IQ data, so I have all my benefits. But of course, then I only have, problems with high-speed signals that I can't decode it anymore. So all those three solutions are not really, workable. Interestingly, we've got a patent on our new idea. I didn't expect that, but it really happened. And with this one, we could reduce the data load by roughly up to 99% if we do it right. And it's really interesting how it works. So if we have a look at that one here, this is a waterfall graph, as you know it from everywhere. You can see a lot of spaces between the transmissions, which is usually noise. And if you make an IQ recording of it, you have all this data on disk, but you don't really need it. So if I extract it, just zoom in, you can see that we simply write all this data as IQ. That's 100% load, we call it that way. So why not replacing the noise with spectra? So if I throw out the noise, I don't send it, I send it as IQ data, I send it as spectra instead, so with an FFT. I can highly reduce the data load, of course, and I still get my timing information, and I can still see what's going on, right? So that's point number one. Then, secondly, you can even reduce that one. Instead of sending spectra, I can send a vector information. So I can say I have a start frequency, stop frequency of the noise, and I just send those information from the start and stop frequency, and the line itself will be drawn on the PC later on, but just by combining the start and stop frequency. And this also reduces the data amount allowed. And finally, we can say that some of the IQ data could be replaced by spectra because I just want to see how it looks like, but I don't want to decode it later on. So then I can also reduce the bandwidth a lot. And finally, I could say that if I identify a special pattern, let's say Wi-Fi, why do I need to transfer that as a spectra information? I could simply say, hey, this is a Wi-Fi at this and this frequency, and just send this information instead. And later on the PC, I pull it from a database and replace it by this optimized vector graph. And that's exactly what we're doing at the fourth step. It also works with noise, of course, because then I don't see a line. Instead, I see a noisy something, and it looks like real. And that's how you reduce the data. And at the end, you get a super idealized spectrum system. So you have all the IQ information you really want to have. You get the spectrum information completely intact, and the time domain is not violated. So it's really significantly reducing the data load, and you have no real losses. And that's really interesting. Of course, you could say, okay, if I have a very bad connection from the receiver to the PC, what happens if, in some cases, over the full spectrum, I get only IQ data? Of course, my transfer over the USB would not work anymore, because at that short moment, I would get a very high data load. And how do I ever overcome this problem? So you can overcome it simply by buffering the data and caching it and compressing it, and at some time you simply release it and then get a steady data flow that's quite capable of your transfer that you have, for instance, your USB 3.0 or so. And that works quite well. So real-life examples, for instance, we have 5 gigahertz Wi-Fi, super high occupied, and the real-life test shows that we can get a 50% data reduction, which is really, really good if you look at that graph. And if we make the wideband monitoring, that's exactly what it's made for. We could, for instance, monitor 8 gigahertz, and at our test with super high occupied bands, we get a 95% data reduction, which is really shocking good. And yeah, that's it so far. Thank you.